So we have seen how to use a divide and conquer strategy to implement a sorting algorithm called merge sort. So now we want to analyze whether merge sort actually behaves better than our order n squared intuitive sorts like insertion sort and selection sort. So in order to analyze merge sort, we first need to look at the merge operation itself. So remember that when we merge two sorted lists, what we do is we take both lists side by side and we keep copying the smaller of the two elements at the head of each list into the final list C. So this was the code that we wrote last time. So basically we have a list A which runs from 0 to m minus 1, and we have another list B which runs from 0 to n minus 1, and we produce the output in a third list C which has indices from 0 to m plus n minus 1. Right? So what we do is we start by putting an index ij into these two lists and index k into the list C, and we compare these two values and we take the smaller of the two values and move it here, and then we move this, and then we keep moving these two indices, and all the while we keep moving k. So the question is, how long does this take? So in each iteration, notice that we add one element to C, right? But the size of C is exactly m plus n, because there are m elements in A and there are n elements in B, and each of them will eventually make it to C. So there are m plus n elements, right? And in each iteration of this loop, the loop that we had before, right? So in each iteration of this loop, one element gets added to C, either in this if or in this if k is incremented. Right? So this list, as you can see, k will make progress in every iteration. So there is a bound of m plus n steps for this loop, and in the loop we will, if you count very carefully, we have a comparison, we may have one more comparison, we have an assignment and so on, but you can check that there are no more than 7 steps involved. So some constant number of steps regardless of which branch we take in this, right? So we have m plus n iterations, each of which has some constant number of steps. So we have overall order m plus n steps. But m plus n is of course bounded by 2 times the maximum of m plus n. So we can just say that this thing takes order of maximum m plus n. If m is roughly the same as n, which will typically be the case in merge sort because we split it in half, so the two will differ by at most 1 in terms of length, then we find that merging is a linear time operation. So if we want to merge two lists, it takes time proportional to the length of the two lists together. So now coming to merge sort itself, what we want to do is we want to take a list of size n, right, and we want to split it into two lists of size n by 2, right, and then we sort these separately and then we merge. So in order to do this, it's very clear that if we look at Tn as the time taken by merge sort on an input of size n, then this requires us to sort two lists of size n by 2, and then as we have seen, it takes order n time in order to merge them. Now, in order to compute this T of n explicitly, we will assume that n is a power of 2. Now, it turns out that merge sort does not in any way require n to be a power of 2, not even an even number. If it is not even, then when we split into two parts, they will not be equal, because we cannot split an odd number into two equal parts. But it doesn't matter, the algorithm will still work correctly. This assumption that n is 2 to the k is only a simplification for us to be able to come up with a nice calculation. So we have two problems of size n by 2, 2 times t of n by 2, and then we have a merge of n. So how do we solve something like this? Of course, we also have a base case which says that when we have only one element, it takes no time except to just check that you have only one element. So t of 1 is 1. Right? So if you have a solution, an expression like this, two recurrences like this, then how do we solve them? Right? So the basic idea is to keep the simplest way to do it. Of course, you can come up with more sophisticated ways which we will not go into right now. But one simple way is to just keep expanding using the same analysis, the same expression, until you come down to the base case. So we start with the base case t1 equal to 1, and the general case Tn is 2 times t of n by 2 plus n. So now what we can do is we can use the same equation to expand t of n by 2. Right? So if we expand t of n by 2, then we find that t of n by 2 becomes 2 times t of n by 4 plus n by 2, because I take whatever is here, divide by 2, so n by 2 is n by 4, and I take whatever is here and plug it in here, so n by 2 comes in. Now if I expand this out carefully, then this 2 and this 2, rather than write it as 4, I will write it as 2 squared. I will also observe, and this will be useful, that this 4 is again 2 squared, right? And then this n by 2 is multiplied, so this n by 2 is multiplied by 2. So I get 2 times n by 2, so that's n plus n, so I get 2n. Okay? So it's not an accident that I have 2 squared and 2n. As we will see, if you do one more step, now if I take this expression t of n by 2 square and I apply the same rule to this, right, then this t of n by 2 squared expands out like this, right? It's n by 2 squared divided by 2 is n by 2 cubed. So I get 2 times t n by 2 cubed plus n by 2 square. Now this and this will cancel, right? So I get 1 n here, I already have 2 n's, so I get 3 n's. And this 2 into 2 square I will write as 2 cubed, right? So I have gone from 2 squared t n by 2 square plus 2n to 2 cubed t n by 2 cubed plus 3n. So it's easy to verify that if you do this j times, you will have 2 to the power j times t of n by 2 to the power j plus jn, right? So now when do we reach the base case? We reach the base case when n by 2 to the power j goes to 1. So when does this happen? Well, n by 2 to the power j is equal to 1. It means that 2 to the power j is equal to n, right? So j is nothing but log of n to the base 2, right? So we will always use log n in general to mean log of n to the base 2 unless otherwise specified. Okay. So after log of n steps, we end up with something which looks like this, right? It has 2 to the j t n by 2 to the j plus jn. After log n steps, j is log n, so I have 2 to the log n, then t of n by this, so this is t of 1 now, so this is just 1, so this multiplied by 1. And then I have j times n, so j is log n, so j is log n and n is n, right? So I have, after doing this expansion log n times, I end up with 2 to the log n plus log n times n. 2 to the log n by definition is just n, right? Because that's the definition of log. That is the exponent of 2 which gives you n. So this is n, and I have this gives me n log n, and we know from general things that n is big O of n log n, so this is bounded by 2 times n log n. So we can say that overall merge sort takes times O n log n, right? So we have achieved a significant improvement, because remember that so far both insertion sort and selection sort were O n square, and we have come down from O n square to O n log n by using this divide and conquer strategy. So why is this a big deal? We saw right at the beginning that O n log n is much more efficient than O n square. Okay? If we assume, as we have said, that a reasonably standard desktop machine can do 10 to the 8 operations per second, then the size of the feasible input of what we can sort with a sorting algorithm goes from 10,000 for an n square algorithm to 10 million or 1 crore for an n log n algorithm. So therefore, if we really have to sort large volumes of data, n log n makes it feasible for us to do so in a reasonable amount of time, whereas n squared would take years, as we saw before. So before we conclude, there are some nice things to notice. So this merge operation which we have used in merge sort is actually a very useful operation on any sorted list. Right? So one thing that we do in merge is that we actually combine the lists without losing anything. So if we merge two lists such as say 1, 2, 4 and 2, 3, 6, then in our final thing we will have 2 copies of 2, okay, because there are 2 copies, and then 3, 4, 6. Right? So sometimes we may want to not have this. We may want to keep only 1 copy. We might want to treat these as sets. So if I take this as a set 1, 2, 4 and the set 2, 3, 6, then the resulting union of the 2 sets is 1, 2, 3, 4, 6 with only 1 copy of 2. Well, we can easily do this in our merge procedure by just saying that when I find, so earlier we had 2 cases. We had AI less than or equal to bj, and then we had AI greater than bj, right? So in the first case we copied from ai, in the second case we copied from bj, and in either case we only incremented either I or j along with k. In this case we say that if the two sides are equal, we keep one copy of it in the final list, but we skip over both these copies. We increment all 3 pointers, right? So if we are at this position and this position, right, then in our output we will copy a 2, and then we will move this pointer to the right and this pointer to the right, so I don't copy 2 twice, right? So this is one thing that we can do. The other thing that we can do is to intersect two lists. So if we again have 1, 2, 3, and maybe 2, 3, 6, right? Then maybe we want to make sure that we have in our output only 2 and 3, right? So now what we do is when we start looking at these two, if they are not equal, then obviously they are not in the intersection. But which one should we leave? Well, 2 could still be there because 1 is smaller, so we move this pointer right. So if AI is smaller than BJ, we increment I. Now we say when AI and BJ are the same, we will, as we did for union, we will move the 2 out, and we will merge, we will move both pointers. So now both pointers come to this position. Now again we will say that we have 3, and we will continue, and then when we see the other way around, if BJ is smaller than AI, we will increment J and not I, right? So the important thing to note is that merge is a very generic operation. We can do what we did earlier, which was to actually shuffle the 2 sorted lists into one big sorted list where no elements are lost, or we can remove duplicates while we are doing it, treat it as a set union operation, or we can only keep the common parts, which is a set intersection operation. Okay? So to check that you have understood this, maybe you should try out the following exercise. So supposing we want to do what is called list difference. So set difference is sometimes written like this. So if I take the set 1, 2, 3 and the set say 3, 4, 6, right, and I ask the set difference, it says whatever is in A but not in B. So the answer should be, in this case, 1 and then 2 but not 3, because 3 is there in both. Okay? So you can do the same thing for lists. So for example, if I had the list 1, 2, 3 and the list 3, 4, 6, then I might want to keep the list only 1, 2. So just check whether you can adapt merge in the way we have done now for union and intersection in order to list difference. So merge sort, though it is an order n log n sorting algorithm and therefore is significantly faster than insertion sort or selection sort, it does have some shortcomings. The main problem with merge sort is that it requires extra space. See, when I take A and B and I merge it into C, it's almost impossible to do this without storing the merged array in a separate place. Because if I start merging in place, then the sorted order of A and B gets messed up, or I have to keep shifting things, and so the merge is no longer linear time. So if I want a linear time merge of A and B, this can only be achieved by using an external list of the size which is the sum of the two lists in order to store this. This means that if we are sorting large arrays, also extra space is being used, because I have to keep duplicating the space in order to do the merge operation. And of course, the other thing about merge sort, which is very difficult to overcome, is that it is inherently recursive. I mean, there is no way to actually easily make it iterative, because we need to construct the sorted things and then merge them. So we need to store these recursive solutions at each point in order to combine them, right? So the recursive call and return can be expensive also. So although merge sort is a very attractive sort in terms of its theoretical complexity, it is not sometimes used in practice because of these limitations, and we will see how to overcome this in some other way. So the main reason we need extra space in merge sort is because of the merge operation. As we saw, in order to combine A and B into a list C in linear time, you need extra space. Now suppose, and the reason this happens is because we could have something like the left side could be say 2, 4, 6, and the right side could be say 1, 3, 5. And now we need to take things from both sides. So sometimes I need to take something from here, then I need to take something from here, then I need to take something from here, and so on. Right? So though each of the two halves is sorted, there are elements from the left which must go to the right, and there are elements from right that must go to the left. So now, if we could come up with a way to avoid doing this, so that everything in the red part is smaller than everything in the green part, then once I have sorted the red part and I have sorted the green part, then automatically everything in the red part stays to the left of everything in the green part. Right? So if I had instead of this, if I had on the left, I had started with say 2, 1, 3, and on the right I had started with 6, 4, 5, and then I had locally sorted these things. So I had got 1, 2, 3, and then here I had got 4, 5, 6. Then after this, if I had guaranteed that the split was such that everything on the left is smaller than everything on the right, after doing this divide and then solving the sub problems, there is no combination of it. There's no need to merge. Okay? So our next sorting algorithm will look at a strategy to implement this idea.